very large menu. Thank you very much for this invitation. Thank you for EHRA and AFNET to organize this meeting and take us back to the real life. So I've been asked to speak about artificial intelligence and atrial fibrillation, and as a cardiac physiologist, I will not go in detail in all the computer process, but just remind that this artificial intelligence, it's a very old process starting in the 50s when researchers want to pin down the mechanisms, the brain mechanisms for memory. And then there is a series of development in this artificial intelligence with machine learning, which is the most basic approach. You teach a computer to recognize a cat or a dog. And then this more recent development, which is a deep learning, which consists of a series of convolutional layers that reproduce the neural networks and which are actually extremely developed. And the major growth of artificial intelligence also starts with the development of internet and access to a large data set. So for what concerns atrial fibrillation, what explains this exponential use of artificial intelligence? First thing is the signals, which are the two pillars for atrial fibrillation, the electrical signals and the cardiac imaging signals that are extremely suitable for artificial intelligence processes. And many of these studies have used these two tools clinically used for AF management. The other explanation for this growth is the large databases that have been created, and notably the PhysioNet that give access to a very large number of, for instance, electrocardiogram, and explain that many of the studies have been used this approach. So on this time scale, you can see the fantastic growth of the number of studies using artificial intelligence in the context of atrial fibrillation, mainly about detection, risk prediction, AF management, and others. So I just would like to go through some examples, and I will come back to this issue of AF and stroke. So this all these studies have used two major processes, this deep neural network that I said before. I think what is important to remind about this deep neural network is first, it can use raw signal. The direct electrocardiogram can be used for this study, which is different with the machine learning, where you need to have a features signal. What is also extremely important and probably will feed the discussion, it can analyze hidden signature of the disease, which is not analyzed directly by the signals. But it has two constraints, which is you need to use very large amount of data. And second, there is a black box. And today, a large field in artificial intelligence, I will give you an example, is to try to understand the black box generated by these neural networks and understand how these networks has worked and, for instance, predict a risk of outcome in the context of atrial fibrillation. The other methodological aspect of this type of study is, of course, the data, which raise a number of difficulties, not just the large amount of data, but also the access to the data pipe, the sharing, the RGPD. And there is a huge need for manpower and to proceed this data, to digitalize the data, to use the data. And this is probably one other major limitation. So one example of an application of artificial intelligence in AF is to help for ablation procedures. And the study of the group of Marianne show that you can learn a computer to analyze electrical signal recorded inside the atria during ablation procedures, to identify beside pulmonary vein other area of responsible for the atrial fibrillation. And so they developed a series of layers to study the signal generated by rotors in the wall of the atria. And they found that they can teach the computer and predict which area during the atria can be ablated beside PV, which a high prediction of a PV loop. And they also open the black box and observe that the neural networks generated by the machine also have its own logic to predict the risk, the significance of the electrical area. So this is a sort of very straightforward application. But the other, I think, major challenge raised by artificial intelligence and AF is back to the question of the first session, which is to link the risk of AF and stroke. And so from a pathophysiological point of view, the risk of stroke and AF is extremely complex. We have discussed that. There is, of course, the loss of the normal sinus rhythm and the fact that in fibrillation, the atria lost normal contraction. And there is also a group of biological defects which are responsible for hypercoagulable state. There are local mechanisms, but there are also systemic mechanisms that probably have to do with this atrial cardiomyopathy. So the first challenge, and we also discussed that very in detail this morning, is that a number of these stroke without a cause are probably due to atrial fibrillation that we need to screen. So I will not go in detail with this too elegant study, but what the artificial intelligence are bringing to this field has been shown by this study published in the Lancet from the Mayo Clinic, and they developed a neural network to analyze electrocardiogram in sinus rhythm from a very large cohort of patients. They divide this cohort in two groups, one group without episode of atrial fibrillation, and the other group with episode of atrial fibrillation. And they found that they can, with this algorithm, analyze the electrocardiogram during sinus rhythms and predict the risk of AF. So again, these neural networks can see hidden signature of the disease and predict with a surface electrocardiogram patient with a high risk of AF. So this open, and again, the discussion about the screening of atrial fibrillation and artificial intelligence clearly can be one answer. So they show here the prediction with this ROC analysis with this new algorithm that if you analyze the electrocardiogram, you have a very high prediction of the risk of atrial fibrillation. But we discussed already with the loop study and with the stroke stop that increasing the screening of AF may not be sufficient to reduce the risk of stroke, even if you have more patients under anticoagulation. So we're back to this notion of atrial cardiomyopathy, which said that probably there is a hidden disease beyond the stroke and beyond atrial fibrillation, which probably AF is a sort of clinical expression of this atrial cardiomyopathy, which has a lot of underlying mechanisms, local underlying mechanism, and there was a very dense research activity that have described many of the defects, but there is also systemic mechanism, the genotypes, the age, the metabolism. And today there is a very capacity and difficulty to identify this atrial cardiomyopathy before its clinical expression. Just this study that you're probably aware of, but that show that if we can have biomarkers to identify this atrial cardiomyopathy, we can predict the risk of atrial fibrillation. It is a study performed in a group of patients undergoing cardiac surgery, for which there was a sampling of the left atria obtained during cardiac surgery. They performed a number of analyses, notably genomic analysis, transcriptomic analysis, and they found that, for instance, all the marker of extracellular matrix remodeling of fibrosis is probably an early indicator of the remodeling of the atria, of the risk of atrial fibrillation. So back to the question of artificial intelligence. Today, the question is, can we use all these biological markers or new biomarkers of atrial cardiomyopathy to predict the risk of AF and of stroke? And this is not directly in the context of atrial fibrillation, but I think it's one very important direction which is actually undertaken. It is the group of Antoniades in Oxford. They have performed this very elegant series of studies showing that you can analyze the texture of the adipose tissue around the coronary artery, and the texture of this adipose tissue around the coronary artery tell you about the oxidative stress inside the artery, inside the atheroid plaque. They call that the fat attenuation. Then they use a strategy of machine learning to train and teach the CT imaging to recognize these adipose tissue textures and show that it's a very powerful biomarkers to predict the outcome after an ischemic episode. And today they extend this approach to the atrial cardiomyopathy, because you know that there is this fat around the atria, and that this fat turned to be one of the mechanisms contributing to the development of the atrial cardiomyopathy. This fat tissue also has different state depending on this inflammation, oxidative stress, metabolic stress. And so they developed in this very large orphan study a machine learning approach to teach the imaging of the texture around the fat of the tissue to see whether we can have an early diagnostic of the atrial cardiomyopathy. Another approach which is actually undertaken is to use other cardiac imaging to improve the detection of this atrial disease. Here it's the analysis of the strain of the atria using MR imaging, and we show, and with others, that the strain of the atria, of the myocardium, it's a very precise biomarkers of the remodeling of the myocardium. And for instance, it's proportional to the fibrofatty infiltration of the atrial myocardium. And today there is an effort to develop transfer learning in order to make available this fine analysis of the local atrial strain, not by the MR imaging, but by the echo, which is more clinically useful. And again, to try to develop new tool to identify early this atrial cardiomyopathy. And so just to finish, we have create with some colleagues in this audience, with AFNET, a consortium, a European consortium called Maestria. The aim is to develop a platform using machine learning, artificial intelligence to provide a digital platform to help for the diagnostic of the atrial cardiomyopathy, the risk of stroke and AF, using this machine learning process to teach clinically used tools with all this development in our understanding of the pathophysiology of AF, stroke, and atrial disease.